Welcome to our presentation on basic regression analysis. This session is designed for students and researchers looking to understand the core principles of regression and how to apply them using EViews. As the EViews documentation states, single equation regression is a cornerstone of statistical analysis, offering a powerful way to understand relationships in data. Our goal today is to bridge the gap between economic theory and empirical practice. For instance, an economic theory might suggest that education increases wages. Regression analysis allows us to estimate exactly how much an additional year of schooling increases a person's income on average. So let's start by defining the fundamental problem we are trying to solve with regression.
At its core, econometrics is about moving from qualitative statements to quantifiable insights. We often start with an economic theory, such as the idea that marketing spend affects sales revenue. But how much does it affect it? The challenge is to formalize this theoretical relationship and then seek empirical evidence to quantify it. Our primary goal with regression analysis is to take a qualitative idea, represented as x affects y, and translate it into a precise mathematical model, like y equals beta 1 plus beta 2x. This equation allows us to quantify the marginal contribution of one variable, x, to another, y, while holding all other influencing factors constant. A critical aspect of this quantification is to distinguish between causal inference and mere correlation. We want to determine if changes in x actually cause changes in y, or if they simply tend to move together without a direct causal link. For instance, ice cream sales and crime rates are correlated because both typically increase in the summer, but one does not cause the other. Regression helps us build models that can control for such confounding factors, moving us closer to understanding true causal relationships.
Choosing the right econometric model depends heavily on the nature of your data, especially your dependent variable. This flowchart provides a simple, structured decision-making process to guide your selection. First, identify the type of your dependent variable. Is it continuous, discrete with a binary outcome like 0 or 1, or a time series? If your dependent variable is continuous, meaning it can take any value within a range, and the relationship you're modeling is linear, then ordinary least squares, or OLS, is the appropriate method. As highlighted in our OLS checklist, this method is ideal when your data is cross-sectional or time series, the relationship is linear, and the dependent variable is continuous. However, if your dependent variable is discrete, often representing a binary choice like yes or no, models such as Logit or Probit are more suitable. For situations where you're analyzing data collected over time and primarily interested in its temporal dynamics, such as forecasting, you would typically use ARIMA or VAR models. Understanding these distinctions ensures you apply the most appropriate and robust analytical technique for your specific research question. OLS, in particular, is the foundation for many other advanced techniques, so let's now see how it fits into the broader system of methods available in a typical software package like EViews. In EViews, least squares, or LS, stands as the central, foundational method from which a wide array of more advanced econometric techniques evolve. Methods like two-stage least squares, or TSLS, address endogeneity issues, while ARCH models are used for analyzing volatility or heteroscedasticity. The generalized method of moments, GMM, provides a more robust approach under weaker assumptions, and ARIMA is tailored for time series analysis. Even Logit models, designed for discrete dependent variables, build upon similar estimation principles. EViews provides two primary ways to specify your models. For simple, linear models, you can use the list method, essentially just listing your variables. However, for more complex relationships or nonlinear equations, the formula method allows you to explicitly define the mathematical structure. For instance, modeling consumption as a simple linear function of income could use the list method, but if you introduce a squared income term, the formula method becomes necessary. Understanding these methods is crucial as we delve deeper into the mathematics of OLS. This is the fundamental equation for a simple linear regression model. Let's break it down.
yi is the dependent variable, also called the endogenous variable. This is the outcome we want to explain. Xi is the independent variable, or exogenous variable. This is the factor we believe influences y. The terms beta 1 and beta 2 are the parameters, or coefficients, that we need to estimate. Beta 1 is the intercept, which is the value of y when x is 0. Beta 2 is the slope, which measures the change in y for a 1-unit change in x, our marginal effect. Finally, ui is the stochastic error term. It captures all other factors that affect y, but are not included in the model. The difference between the actual value yi and the predicted value y hat I from our model is called the residual, denoted by ei. In our sales and marketing model, yi would be the sales of a specific store, xi would be its marketing budget, beta 2 would be the return on each marketing dollar, beta 1 would be the baseline sales with 0 marketing, and ui would represent other factors like local competition or location. For our estimates of beta 1 and beta 2 to be reliable, a set of assumptions must be met. Let's examine these critical assumptions next.
The reliability of OLS estimates is fundamentally built upon a set of conditions known as the classical linear regression model, or CLRM, assumptions. These assumptions are the structural pillars that support the entire edifice of our model's validity. They include key elements like linearity in parameters, ensuring our model is correctly specified, and the principle of random sampling, which is crucial for external validity. We also assume the error term has a 0 mean, a constant variance, known as homoscedasticity, and that errors are independent of one another, meaning no autocorrelation. Finally, for hypothesis testing, we often assume normality of errors. It's critical to understand that if any of these assumptions fail, the consequences can be severe. Our estimated coefficients might be biased, systematically misrepresenting the true relationships, or our p-values could become invalid, leading us to draw incorrect conclusions about statistical significance. For instance, a violation of homoscedasticity or heteroscedasticity means our standard errors are wrong, even if coefficients are unbiased. However, when these assumptions do hold, OLS provides us with the best linear unbiased estimator, or BLUE. This means it's the most efficient estimator among all linear and unbiased estimators, giving us the most precise coefficients possible. Now, assuming our model meets these essential assumptions, we can confidently move on to interpreting the coefficients we obtain from our estimation. Once we have our estimated equation from a regression analysis, the crucial next step is to interpret what the coefficients actually mean. Let's take a classic Keynesian consumption function as an example. Consumption equals 100 plus 0.8 times income. Here, the 100 represents the base level, or intercept. It signifies the autonomous consumption, or how much an individual would consume even if their income were 0. The 0.8 is the marginal contribution of income to consumption. This means that for every $1 increase in income, consumption is expected to increase by 80 cents, on average. To systematically interpret any regression output, we use a 3-step reading guide. First, we examine the sign of the coefficient. Is the relationship positive or negative, and does it align with our theoretical expectations? Second, we assess the size of the coefficient. Is the economic impact meaningfully large or trivial? Finally, we check the significance by looking at the p-value. Is the coefficient statistically different from 0, giving us confidence that the observed relationship isn't just due to random chance? Following these steps ensures a thorough and reliable interpretation of our model results. Welcome to the digital cockpit of EViews, where we execute our econometric models. There are 2 primary ways to initiate an estimation in EViews. First, you can navigate through the menus by selecting Quick and then Estimate Equation. This method is user-friendly, especially for beginners. The second, and often faster method for experienced users, is to directly type your command into the EViews command window. As a pro tip, typing ls for least squares in the command line allows for quick and efficient model specification. The general syntax for the least squares command, or ls, is to first list your dependent variable, followed by your regressors. Remember to explicitly include C for the constant term if your model requires an intercept, and variables like T for a time trend, if applicable. This direct approach streamlines the modeling process, allowing for rapid iteration and testing of different specifications. Here we see the practical interface in EViews for specifying and running a regression. This screenshot of the Equation Estimation dialog box demonstrates how we input our model. Following our discussion on the NYSE volume analysis, we've entered log of volume C at trend into the specification field. This is an example of the list method, which is ideal for straightforward linear regressions. Log of volume is our dependent variable, C denotes the constant term, and at trend is the built-in time trend variable. Below this, you can see that LS least squares is selected as our estimation method, consistent with our objective. The sample period is also specified, from 1888 to 2004. This list method is simple and efficient for linear models. For more complex or nonlinear equations, EViews provides a formula method, which allows explicit equation definition, such as y equals c1 plus c2 times x squared. Let's begin our case study by analyzing the trading volume on the New York Stock Exchange. The very first and most crucial step in any empirical analysis is to visualize your data. Plotting the data, as shown here for the logarithm of NYSE volume, helps you identify key features that will influence your modeling approach. When reviewing such a plot, always have a checklist in mind. First, look for seasonality, which are any repeating patterns within a consistent time frame. Second, identify clear trends, such as the prominent upward movement in log volume visible over time in this chart, spanning from 1888 to 2004. This strong trend suggests that a time trend variable might be critical for our regression model. Third, keep an eye out for structural breaks, sudden and persistent changes in the data's behavior. Finally, inspect for outliers, which are extreme, isolated observations that could disproportionately influence our results. Understanding these features from a simple plot is fundamental before proceeding to statistical estimation. Now that we've explored our NYSE volume data and identified a clear trend, it's time to run the actual regression estimation in EViews. The command we'll use is ls log of volume c at trend. Let's break down this syntax. The ls prefix tells EViews to perform a least squares regression. Following this, log of volume is our dependent variable, the outcome we are trying to explain. We then explicitly include c, which represents the constant or intercept term in our regression model. Finally, at trend is a very convenient built-in EViews regressor that automatically generates a time trend, essentially assigning values like 1, 2, 3, and so on to each observation. This entire command specifies an OLS regression where the logarithm of trading volume is modeled as a linear function of a constant and a time trend. Once executed, EViews will generate an output table detailing our estimation results, which we'll learn to interpret next. This slide displays the standard EViews output for our regression model. Let's examine its key components. The coefficient column provides the estimated values for our model parameters. The coefficient for C is the intercept, and the coefficient for at trend is the slope. Next, the prob column shows the p-values, which are critical for assessing statistical significance. A p-value below the conventional threshold of 0.05 indicates that a variable has a statistically significant effect. For instance, the p-value for at trend is 0.0000, confirming its strong significance. Lastly, the r-squared value measures the model's goodness of fit. An r-squared of 0.85, as seen here, means our model explains 85% of the variation in the logarithm of NYSE trading volume. Now that we understand how to read these numbers, the final step is to translate them into a meaningful economic interpretation. Based on our EViews output, the estimated equation for the log of NYSE trading volume is log of volume equals minus 2.63 plus 0.017 times trend. The key insight here comes from the trend coefficient, which is 0.017.
Since our dependent variable, volume, is in logarithms, we can interpret this coefficient as a percentage change. This means that NYSE trading volume has been increasing by approximately 1.7% per quarter, on average, over the period analyzed. To assess the reliability of this finding, we look at the p-value. The p-value for this trend coefficient is 0.0000, which is significantly smaller than the common threshold of 0.05. This leads us to confidently conclude that this upward trend is statistically significant, meaning it's highly unlikely to be due to random chance. As a quick rule of thumb, if the p-value is less than 0.05, we reject the null hypothesis, indicating that the variable is significant. Another useful rule is that if the absolute value of the t-statistic is greater than 2, it generally implies significance at the 5% level. With our interpretation complete, we now move to crucial diagnostic checks to ensure our model is robust.
After estimating our model, post-estimation diagnostics are crucial for validation. A primary tool is the analysis of residuals, which are the differences between the actual and fitted values. Ideally, these residuals should be white noise, meaning they are random and show no discernible pattern. If you observe long runs of positive or negative errors, it's a strong indicator that your model is misspecified and isn't fully capturing the underlying dynamics of the data. Another important diagnostic is the Durbin-Watson statistic, which specifically checks for serial correlation in the residuals. This is vital because serial correlation violates one of the key classical linear regression model assumptions, compromising the reliability of our inference. Once we're confident in our model's health based on these diagnostics, we can then confidently use it for forecasting. The model projects future values, and importantly, we generate confidence intervals around these forecasts to quantify and represent the inherent uncertainty in our predictions. Thank you for joining this session on basic regression analysis. We hope it has provided you with a solid foundation and practical insights. For those who wish to delve deeper, we recommend the classic econometrics texts by Pindick and Rubenfeld, Johnston and DiNardo, Wooldridge, and Green, which offer comprehensive coverage of theory and application. As for your next steps, we highly encourage you to practice what you've learned by reproducing the NYSE example in EViews. Hands-on application is key to mastering